Hello, this is our first example using POCOE. In this example, we're back at the Burj Khalifa. Using principles of energy, we're going to determine the impact velocity of our favorite crate full of fruit if we drop it from the top of the Burj Khalifa. And I went ahead and drew a picture. It's actually kind of a very similar picture to what we had before. And so actually going into this, let's just note this. Recall, from projectile motion, we determined the impact velocity for a horizontal launch. So this isn't being launched, it's being dropped, which means it has no initial velocity, as we put in our knowns. But just like projectile motion, well, really, free fall motion is just a subset of projectile motion, but that means the acceleration is only in the y direction. And for a horizontal launch, there was no initial vertical velocity. So I think our vertical velocity that we determined for the impact velocity from that example should end up being the same as the velocity we calculate for this. Sorry about that. So anyway, the point is, we probably already know the answer, but now we're going to use POCOE to get there instead of the big three. And I think you'll see that this ends up being a little bit less work relative to what we did with the big three. So we know that when we drop this, it will eventually get down to here with some impact velocity like so. But we're not going to build a toolbox this time. We're going to use POCOE. So we'll say using POCOE. And our kind of thought process, I'll walk you through it. To use POCOE, we're going to choose 2 points in our picture and compare the total energies. One of the points we're going to choose is the point that we have information on. We know the starting point, the height of our crate. And so we're going to call this 1. We'll say 1 is the top. And then we're going to compare the energy at the top to the total energy at the bottom. We know, due to the principle of conservation of energy, that once the crate somehow magically gets to the tip of this building, it will have some amount of energy. That energy will be potential energy, and that energy will now be with the crate until it gets transformed into some other kind of energy. Dropping the crate allows the force due to gravity, the weight of the crate, to act on the crate, causing it to free fall, which you knew. But instead of thinking it as just being accelerated by gravity, what we really want to think about now is what the energy is experiencing. It had all types of potential energy up at the top, and as the weight force acts on the crate, that weight force does work on the crate. It is acting in the same direction as the displacement. And so energy is being transformed. So we could note the crate starts with potential energy because it's on the surface of the earth and it's lifted from the surface of the earth, so it has a height. So the crate starts with PE. Weight does work on the crate, and that work converts PE into the energy associated with motion, kinetic energy. And by the time it gets to the ground, just an instant before it collides with the ground and new external forces do new work on the crate, all that potential energy will have been converted to kinetic energy, and that's represented by the velocity that it has at the bottom. So that's our thought process. We're following the energy and the energy transformation. But this is how we use POCOE every time. We always start with the total energy at some point equal to the total energy at any other point in our system. Well, we're going to choose the top and the bottom. So the total energy at the top is equal to the total energy at the bottom. Now the total energy could be potential energy at the top or kinetic energy at the top. And the same for the bottom, potential energy at the bottom and kinetic energy at the bottom. Now this may seem a little bit excessive because we just discussed that it starts with potential and ends with kinetic. But if I give you a problem that the body starts with potential and kinetic, I don't want you to skip a step because this will allow you to keep track of all the energies. So we know from the previous video that PE is always mgh, and it would be the height at the top. KE is always 1/2 mv squared, but it would be v at the top. And that has to equal the same but for the bottom. So we have mgh bottom plus 1/2 mv bottom squared. But we do know that at the top, the crate starts from rest, it's dropped, and so the velocity at the top is 0. And we know that the bottom means that the height has gone to 0. That's what classifies the bottom of the building. And so we can rewrite this without our quantities with 0 in them. So now we have mgh top equal to 1/2 mv bottom squared. And just like we thought about at the beginning, we'll have potential energy at the top and kinetic energy at the bottom. That's what POCOE has shown us. Now we can do a little algebra and solve the problem. If we divide both sides by mass, the masses turn to 1. And I can multiply both sides by 2 because we're looking to solve for v, right? So we end up with 2gh top equals v bottom squared. We'll square root both sides and we can get the solution. Now we'll substitute our values. G and mgh is always positive, don't forget. And so this will give us a velocity at the bottom equal to 128 meters per second. But I tried to put this in our notes to remind us. This is asking about a velocity, and the kinetic energy yields a scalar. So we need to use our picture and say, well, it looks like v impact is downward. We started this from some positive height, so we kind of made down negative. And so that means in our coordinate system, this velocity would be negative and in the y direction. So to really get full credit, we'd have to represent it as a velocity, and our picture really helped us with that. But that's our first example using the principle of conservation of energy, or what maybe you'll all start to refer to as POCOE.